So we are going to do these questions one by one. And these questions, I gave them in the WhatsApp. The WhatsApp groups, they are there. We posted them like 2 hours early. Then in the WhatsApp channel, they are there. We posted them sometime. So I'm going to do those numbers and I'm going to be explaining for you the tricks that we talked about earlier on. And by that, after that, I believe you guys would have understood this aspect of organic synthesis. So for those of you who didn't receive them, or if you're not in our WhatsApp groups, please take a screenshot of that. Take a screenshot of that. Those are the first five numbers. Then you take a screenshot of the next numbers, the next 5 numbers. We shall first start with those 10. We shall start with those 10. Okay. So let us start the organic synthesis. Now, organic synthesis is going to be tested in your organic chemistry, whether you like it or not. It is going to be tested, but the principles that are governing it are going to remain the same. So the first question was requiring us to synthesize the questions are in the WhatsApp group. So the first part is saying we are synthesizing. First part of the question, we are synthesizing that compound. Synthesizing that from 1-phenyl ethanol. From 1-phenyl ethanol. So we are carrying out a synthesis. We are carrying out a synthesis. So you are moving from these two to that. So we are starting from 1-phenyl ethanol. So we can draw the structures of that. And the first thing I told us members is that you're supposed to look at the two structures, the two things you have been given. And after looking at them, you try to get to know the difference between them. You get to know the different functional groups between them. Then you remember the reactions that you studied in organic chemistry to be able to do that. So 1-phenyl ethanol is, we can draw the structure of this 1-phenyl ethanol. 1-phenyl ethanol is like that. So we are moving from that compound to this compound. To this compound. Now, by mere looking at those two compounds, you're going to realize that there is a difference between them. First and foremost, this other compound is having very many carbon atoms. The carbon atoms in this other compound, compound 2, are more than the carbon atoms in compound 1. So the thing that you have to do first is to be able to know how are you going to increase on the number of carbon atoms. We looked at that. But because this compound 2 is an alkyne, you're seeing that we are going to use the procedure that is going to involve an alkyne. And we looked at that procedure in organic synthesis part 1. So I am first going to transform this given compound 1 to an alkyne. So how am I going to do it? I'm first going to move to an alkene by carrying out a dehydration reaction. And again, I said that the conditions for the reaction have to be properly stated. So from here, which condition am I going to use to dehydrate? I'm going to use concentrated sulfuric acid. Somebody's raising up their hand this early. I hope it's not a mistake. So the first thing we are going to do is that we are going to prepare concentrated sulfuric, we are going to use concentrated sulfuric acid. You can use concentrated sulfuric acid. The compound we are having is 1-phenyl ethanol. I don't know whether that is giving us, it is from 1-phenyl, it is from 1-phenyl ethanol, sorry. I think I copied that wrongly. It is 1-phenyl ethanol. The compound is 1-phenyl ethanol. You can correct that. I gave you people the question, so be able to look at them very well. So we are going to use concentrated sulfuric acid at a temperature of 180 degrees Celsius to transform that into an alkene. So we shall have an alkene being formed. Double bond, CH, CH2, then I'll put the hydrogen down. Then after me forming that alkene, I want to form an alkyne. But before that, you can first add a halogen. So we can add bromine in the presence of carbon tetrachloride to give us we shall have CBr, then CH2Br. Then after you're going to dehalohydrogenate using excess, you're going to use excess potassium hydroxide in the presence of ethanol. Then we said we heat. And then after you're going to form your alkyne of that formula. So after you forming the alkyne, it is now going to be easier for you to add the number of carbon atoms. And we say the number of carbon atoms we are adding is depending on we are going to add the number of carbon atoms, but the number of carbon atoms we are adding, we are going to put it on the alkyl halide. So the first thing we are going to do here is that we shall first react that with sodium in the presence of liquid ammonia. Then after we hydrolyze it, we add actually the Grignard's reagent. The Grignard's reagent shall have CH3, CH2. We shall add the alkyl halide, sorry. Then after adding that, we shall have our compound. Fully shall have the compound there. So we shall have that compound. So that is the synthetic route. That is the first synthetic route. You first have to go to an alkyne, then after you add the number of carbon atoms basing on the reaction that we gave. Then also, it would be another way that would form an alkyne here. Let me now use a blue ink. From here, we would convert that to a carbonyl compound by using an oxidizing agent. Then after, we shall form a dihalide by adding PCl5 to form for us that Cl, Cl, CH, CH3. Then after, this dihalide can lead us directly to that by dehalohydrogenating. So from the alcohol, you can move to that by using an oxidizing agent. So we can use that oxidizing agent. Then we heat. We said whenever we are using oxidizing agents, we heat. Then we can convert that to that using PCl5 to form a dihalide. Then from this, we are still going to dehalohydrogenate to form for us an alkyne. In the presence of ethanol, then we heat. Then after, you do the needful to increase on the number of carbon atoms. So that is the first synthetic pathway we are taking. So this one here, we are having the concept of increasing on the number of carbon atoms. So that is the concept we are employing there. I gave the questions in the WhatsApp group. Somebody just, maybe let me allow people to take screenshots. For people who are not in our WhatsApp groups, it's okay. You can do that. The question is clearly saying 1-phenyl ethanol. I just made a mistake to put ethanol, but it is 1-phenyl ethanol. So you can take a screenshot of these first 5 parts, the first 5 questions. Take a screenshot of that so that you'll be following. So before every question, you can note it on a piece of paper, then you follow. Okay? Then also that. Take a screenshot of that also. Okay, admin desires, put those questions on the chat. Please get them on the chat. That is the first synthetic pathway we have looked at. From 1-phenyl ethanol. Okay, that is the first part. Another serious warning. Make sure that you don't touch that pen-like structure. Admin desire, please keep on giving us that. Keep on giving us that caution on the chat. Some people here do not listen. The second question we are looking at. The second question, we are synthesizing that compound. Let me draw the compound there. From benzoic acid. From benzoic acid. So we are synthesizing that compound from benzoic acid. Now, the moment you look at this first compound, it looks complicated, but you're going to realize that this compound comes from the reaction between carbonyl compounds and sodium hydrogen sulfide. So we are moving from benzoic acid. Benzoic acid is a carboxylic acid which is aromatic. So we are moving from that to this compound. I remember the first, one of the guidelines I told you people when we were handling part 1 of organic synthesis, I said that you need to know where your final product is coming from. This final product of ours is coming from a carbonyl compound. It is just coming from a carbonyl compound. That is where the final product is coming from. You're seeing that? So I have to see a way of transforming that into a carbonyl compound. The first thing I can do is that one option that you have is that you can remove this carboxyl. You can remove that carboxyl group. So I can have my benzoic acid there. Then we remove the carboxyl group. How do we remove that? We remove that using soda lime. Then we heat. Then after what happens? We shall have benzene. Then you remember that from benzene, you can be in position to form a carbonyl compound. By doing what? You can form a carbonyl compound using Friedel-Crafts acylation reaction. So I'm going to add an acid chloride here. That is going to be CH3. Now, depending on the number of carbon atoms present, depending on the number of carbon atoms, here you're seeing we only have 1 carbon atom. So that means that we cannot be in position to form an alkyl. We cannot be able to form a carbonyl compound directly. So in this case, the first thing you can do is that you can form also methyl benzene. Methyl benzene can lead us to form benzaldehyde. So you can do that using, in the presence of a halogen carrier, then you form methyl benzene. Then from methyl benzene, you can now form the benzaldehyde. You can form benzaldehyde which is like that. So benzaldehyde here, for you to form it, you have to use a weak oxidizing agent. In this case, we can use manganese 4 oxide in the presence of an acid. Then you ensure that you heat. Then after this benzaldehyde can give us the final product by using sodium, react that with sodium hydrogen sulfide, and you'd form the final product. So we say that this compound, the final compound, is coming from a carbonyl compound. So and the carbonyl compound in that case is benzaldehyde. So you flash back into your head, which reactions are we going to use that can give us benzaldehyde? Remember when we were studying that, we say that benzaldehyde can be produced directly from methyl benzene using a weak oxidizing agent. Then there can also be another option. You can have another option. Or another person can decide to say that from benzoic acid, let me move that compound directly to give me an alcohol. There are people who are already playing around with our screen. Before we started the lesson, I said, don't tamper with that pen-like structure on the left-hand side of your screen. Don't use it to write on the screen because it affects my screen too. Please, guys, let us pay attention. So from here, I can move to a primary alcohol. You can move to a primary alcohol. So we shall have CH2OH. Remember, I remember in the other previous lesson, I say that from carboxylic acids, you can move to primary alcohols using what? Using a reducing agent. So the reducing agent usually used is lithium aluminium tetrahydride in the presence of dry ether. Then this alcohol can also now be converted to a carbonyl compound. We say that primary alcohols can be converted to carbonyl compounds using weak oxidizing agents. You can use a weak oxidizing agent. If you use a strong oxidizing agent, you're going to oxidize it directly into a carboxylic acid. So we can use our weak oxidizing agent there in the presence of an acid, and then we heat. So we are going to form now our carbonyl compound, which is benzaldehyde. Then from benzaldehyde, I can use sodium hydrogen sulfate. This reaction, we looked at it under the reactions of carbonyl compounds, nucleophilic addition reactions of carbonyl compounds. So here you'll have that. You will have CHSO3 Na plus. Then you will have OH down, and we would have formed that compound. So there are very many ways of handling it, but the first thing that you should notice is that this final product is coming from this final product here we are having is coming from a carbonyl compound. So your emphasis should be first to produce the carbonyl compound. So through the series of reactions that you have studied over time, you should be in position to isolate and remember those reactions that give us a carbonyl compound. That give us a carbonyl compound. So that is the synthetic route. You can also be taking screenshots, by the way. You can be taking screenshots. The questions we are going to do are very many. So every synthesis, I'm going to do it probably for like a minute or two, probably 2 minutes or 3 minutes. At least we shall be able to finish very fast. Okay? Now, members, before I don't want people to really mess up. Stop writing on the screen. Please stop writing on the screen. You're disorganizing our screen. Just leave that pen-like structure alone. Now, if you cannot take screenshots, you just leave. You people don't know how to take screenshots on your phones. That pencil that is at the left of your screen, don't tamper with it. You're going to make my screen dirty. And you can also remove that thing. Don't start things that you're not in position to finish. So that is the final product. So question 2. You can take a screenshot of that. Just take a screenshot of on your phone. Don't try to take a screenshot on Zoom. Zoom has no provision for you to take screenshots. So we're looking at the third question. The third question. The third question, we are synthesizing. It is giving us CH3, CH, CH2, OH. Then we are having CH3 from propanol. So we are moving from propanol straight up to that compound. So if you're to write the structure of propanol, like this CH3, C double bond O, CH3. Now, when you're to compare these two structures from the guidelines I gave, if you're to compare these two structural formulae, you're going to realize something. The first difference is that this other compound is having the carbonyl functional group. You're seeing that, meaning you're going to transform this and include the carbonyl functional group. Then you can also look at the number of carbon atoms. You're going to realize that the final product we are forming here is having one carbon atom more than this other initial product, which is propanol. So in one of our steps of the synthesis, you're going to include a step that involves us to increase on the carbon chain. You're seeing that? So what are we going to do? What are we going to do? So from propanol, I can decide to increase on the carbon chain using Grignard's synthesis. I can use Grignard's synthesis. So we can say that from propanol CH3, CO, CH3. We looked at this reaction that increase the carbon chain. What are we going to do? We can add a Grignard's reagent in the presence of dry ether. So we shall add methyl magnesium bromide in the presence of dry ether. And then we are going to form an intermediate. The intermediate will be CH3, C, OMGBr, H, CH3. We don't have an H there, sorry. CH3. Then I will have here CH3. Then after, we are going to hydrolyze that using aqueous ammonium chloride. The ammonium chloride we are using is in aqueous state. So we shall end up forming a tertiary alcohol. Okay. So after that, we have already formed our tertiary alcohol. And you have seen that the number of carbon atoms has increased. But how are we going to introduce in the OH group at the end, the hydroxyl group at the end? One thing you can do is that you can dehydrate it using concentrated sulfuric acid. Concentrated sulfuric acid, then you heat at 180 degrees Celsius. And after doing that, you will form an alkene. So you'll have CH3, CH3, double bond, CH2. And then after me forming that alkene, I am going to add a halogen, but in the presence of an organic peroxide, so that we add it according to anti-Markovnikov's addition. So I'm going to add hydrogen bromide in the presence of, hydrogen bromide in the presence of an organic peroxide. And after doing that, I'm going to form that compound. CH3, CH2, Br, CH3. And then after, the last thing is that I'm going to form now an alcohol. CH3, CH2, OH. Then CH3. So from this alkyl halide to give me an alcohol, we always use sodium hydroxide aqueous, then we heat, and we shall be in position to form that. So that is the synthetic route. That is the synthetic route. That is the synthetic route. Now it requires a lot of wisdom for you to handle that number. You're first of all going to increase on the carbon chain. You add one carbon atom, but what the carbon chain, the increase in the carbon chain is involving a branch. And I remember telling you people that if at all you also want to introduce branching in the carbon chain, you can use a Grignard's reagent. The reaction of a Grignard's reagent with a carbonyl compound. You can also have branching taking place. So that reaction requires some wisdom for you to handle that. But I think you can see the concept. You can see the concept. You can take a screenshot of that. Again, as we are moving on, make sure that you don't play around with the pen-like structure on the right part of your screen. Don't tamper with that stuff. That is question 3. Somebody can take a screenshot of that. Then after, you take a screenshot down. Okay. So that is the third question. And I hope you have picked that concept. When we are introducing branching, usually it is important for you to use a Grignard's reagent of reaction with carbonyl compounds, and that one can give you branching. We are going to question number what? Guys, let's stop playing with the screen. You can play with your screen in any other way, but don't use that pen-like structure. Don't use that pen-like structure. We're now going to number 4. Number 4, we are synthesizing this compound, CH3, CH, COO, H, then OH. But we are synthesizing it from butan 1-ol. butane 1, butane 1 all. Now in this case, butane 1 all, we can first write its formula so that we compare the two. Butane 1 all has the formula CH3, CH2, CH2. There are 4 carbon atoms. That is butane 1 all. Now, we are moving from this compound up to this compound. You're seeing that? So this is the final product. So the first thing in that synthesis, you're going to look at those two compounds and try to see how different are they. This other compound I'm seeing is having a small number. In other words, it's having the number of carbon atoms are less. Meaning that in my reaction, in my synthesis, I'm going to involve a step that requires me to reduce the number of carbon atoms. But also that final product I'm having is having both the carbonyl functional group, the carboxyl functional group, and then the hydroxyl functional group. So what does that mean? That means you're supposed to make a remembrance for a certain reaction. Remember, when we're looking at the reactions that increase on the chain, not the reactions of carbonyl compounds, nucleophilic addition, we said that we can react carbonyl compounds with what? With cyanide, with hydrocyanic acid, and it can give us, that reaction can be important for us to prepare hydroxycarboxylic acids. In other words, a carboxylic acid that has a hydroxy group attached to it. So this one is directly coming from a carbonyl compound. It's coming from a carbonyl compound. But which carbonyl compound is it coming from? It is coming from most likely this carbonyl compound, CH3COH. That carbonyl compound is ethanol. You're seeing that? So we have to see a way of transforming this to that. And as you can see that the number of carbon atoms has reduced. And last time we discussed on the reactions that can reduce on the number of carbon atoms. And the most suitable one that we can use here is going to be ozonolysis. It's going to be ozonolysis. So you can start the synthesis. So butane 1 all, CH3, CH2, 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 OH. I can react that with concentrated sulfuric acid at a temperature of 180 degrees Celsius. It is going to give me an alkene, but the alkene that it's going to give me is going to be symmetrical. That is the alkene that it's going to give me. Some of you people may think that the alkene that it's going to give, it's going to be like this. Some people think the alkene that it's going to give is going to be like that. It cannot be like this. Why? Because in your reaction mechanism, there is going to be a hydride shift, a hydrogen ion shift to form a stable secondary carbonium ion. So the one that is going to be formed is going to be that. It is going to be symmetrical. Try and look at the reaction mechanism and you see. So we are going to form that. So after us forming that, we are going to carry out ozonolysis. Ozonolysis is going to split that compound into two. Remember, we say that we can only use ozonolysis when it is going to give us a single product. That is for a symmetrical alkene. So what is going to happen is that the first thing that I can do, I can react that with ozone in the presence of carbon, tetrachloride at a temperature which is less than 20 degrees Celsius. And that is going to form for us an intermediate. And that intermediate is going to be an ozonide. Like that. It's going to be an ozonide. Then after, we are going to hydrolyze this ozonide. The second part, we are going to hydrolyze it using zinc in the presence of ethanoic acid, shall have ethanoic acid, then we shall also have water. So at the end of the day, you're going to form an aldehyde, CH3COH. Then this aldehyde, we are going to react that aldehyde with hydrocyanic acid. But we say that the reaction of carbonyl compounds with hydrocyanic acid does not take place directly. In other words, hydrocyanic acid is prepared from the reaction between potassium cyanide with dilute sulfuric acid, and then you're going to heat that between 10 to 20 degrees Celsius. And then when you heat that, it is going to give us, when you carry out that reaction, we are going to get this compound, CH3C, CN, then OH, then H. Then at the end of the day, what is going to happen is that this compound, this cyanide group can be converted to a carboxylic acid by refluxing it with acidified water. And then you reflux, and you're going to get your final product. CH3, C, COO, H, H, then OH. But the question, that structure has been modified. The structure has just been modified, and we have something like this. CH3, CH. The question we are having CH, COO, H, then OH. And that is the final product. So whenever we are doing that synthesis, let's normally make sure that our steps are few. I remember saying that whenever you're doing a synthetic pathway, make sure that the steps are few so that the synthesis becomes more efficient and even cheaper to carry out. You're seeing that? So let's use at least a route that gives us not more than six steps. At worst, when the worst comes to the worst, it should be 7 when you don't have any other option. So that is the second part. We are reducing on the carbon chain. And that reduction, we have used now ozonolysis. It has helped us to split that compound into 2. If you're taking a screenshot, do so very fast. You can take that, then you can take that. Now this lesson is going to be available on YouTube, so you can just keep on checking it as many times as possible. Or some of you, if it is your first time, you can start from part 1, which is in YouTube. Then after you do part 2, then you do part 3 like that. So that is the fourth question. That is the fourth question. That is the fourth question. Now these questions are available in our WhatsApp group as a PDF. Okay, so let's look at the fifth question now. Question number 5. Question number 5 is that we are synthesizing an amide from nitrobenzene. Nitrobenzene is like that. Then we are moving from that up to that compound. For those of you that have been following, that have been attending our holiday program, we covered this and we say that this is an amide. That compound is an amide. So if at all you're very confused on how it can come, you can do a retrosynthesis. This amide can come from, it always comes from a carboxylic acid, and that is benzoic acid. So you can easily convert phenylamine to benzoic acid. You can do that conversion. Phenylamine to benzoic acid. So what can we do there? We can, let me go to the next page. I can say phenylamine from phenylamine, I'm going to convert that from nitrobenzene, sorry. The question is saying nitrobenzene. Eh? We are moving from nitrobenzene. It is from nitrobenzene, not phenylamine, sorry. From nitrobenzene there. So we are going from nitrobenzene up to that aromatic amine. So remember we said from nitrobenzene you can move to what? You can move to phenylamine. But how do you do that? You're going to use tin in the presence of concentrated hydrochloric acid. Tin conc hydrochloric acid, then you're also going to use conc sodium hydroxide. Then you're going to heat. Those conditions can make you convert nitrobenzene to phenylamine. It's a reduction reaction. Then after that, you can convert phenylamine to, you can convert it to benzene diazonium salt. You can convert it to benzene diazonium salt. But where did we see that reaction from? We looked at the reaction between the reaction of this aromatic amine with nitrous acid, but does not react with nitrous acid directly. Instead, what we use is that we are going to use sodium nitrite in the presence of concentrated hydrochloric acid. Those two are going to react to form for us nitrous acid in situ. So when you do that, we shall use sodium nitrite, which is like that, in the presence of reacting with concentrated hydrochloric acid at a temperature between 0 to 5 degrees Celsius. It's going to give us a benzene diazonium salt. Then from here, I can form that compound, an aromatic nitrile, which is like that. So which condition am I going to use? Potassium cyanide in the presence of copper 1 cyanide. Then I'm going to warm. This reaction, you can see it under the reactions of benzene diazonium salt. Then from here, you can convert it to a carboxylic acid by using acidified water. Then you reflux. You reflux it with acidified water. Reflux that with acidified water to give me that carboxylic acid, COOH. Then at the end of the day, you're going to add ammonium carbonate. And then you're going to heat it at 100 degrees Celsius. It's going to give you that amide. NH2. And that is the synthetic pathway. Now, this benzene diazonium salt is very important when you're doing organic synthesis. Usually, let me first talk about benzene diazonium salt. Benzene diazonium salt is a very important compound when you're looking at organic synthesis. It looks like that. Benzene diazonium chloride. Or you can more simply just write it like that. Like that. This benzene diazonium chloride is very important when you're doing when you're doing organic synthesis. Benzene diazonium chloride can be converted to chlorobenzene. It can be converted to chlorobenzene. Benzene diazonium chloride can be converted to phenol. Benzene diazonium chloride can be converted to bromobenzene. Benzene diazonium chloride can be converted to iodobenzene. Benzene diazonium chloride can be converted to this phenyl nitrile. You're seeing that? So which conditions are we going to use? Here to convert this, I'm starting from down, you use potassium cyanide in the presence of copper 1 cyanide, then you warm. There is no heating in that case. To iodobenzene, you use potassium iodide, and then you ensure that you warm. To phenol, what you do, you just use water, and then you're going to warm at 50 degrees Celsius. To chlorobenzene, what are you going to do? You're going to use copper 1 chloride in the presence of concentrated hydrochloric acid, and then you're also going to warm. To bromobenzene, what are you going to use? Copper 1 bromide in the presence of concentrated hydrobromic acid, and then you're also going to warm. So this is how important benzene diazonium chloride is when you're carrying out organic synthesis. It is something which is very key when doing organic synthesis. And then from this, you can come up with very many other more compounds in organic chemistry. But where does benzene diazonium chloride come from? The only way you can produce benzene diazonium chloride is from phenylamine. Can come from phenylamine. Which conditions? You'll have you're going to have the conditions. You're going to have sodium nitrite in the presence of concentrated hydrochloric acid, and then you're going to have it between 0 to 5 degrees Celsius. Now, these are also very key when you're carrying out organic synthesis. Make sure you take note of them. Benzene diazonium chloride can give us all those other compounds, depending on what you want. Then you look at this one for iodobenzene. This reaction is the only reaction that can be able to produce for us iodobenzene as far as our syllabus is concerned. So if you're told to synthesize iodobenzene, the only way you can do it is by using that benzene diazonium chloride. You react it with potassium iodide, and then you warm. So that reaction is very key. So what I did is that I could be in position. Now my synthesis exploited this number, that part that I have ticked. It exploited that part. So my synthesis, I first had to move to the benzene diazonium chloride. Then it led me to that, so that I produce the carboxylic acid. But another person would have also done the same synthesis in another way. Let me show you that way. Another person would have said, from the benzene diazonium salt, From that benzene diazonium salt, I'm starting from the middle. I don't want to start from the beginning. One person would have also produced phenol by reacting that with water, and then you warm. And that one would give us phenol. Then from phenol, somebody will decide to remove that hydroxyl group by using zinc dust, and then you heat. And that will form for us benzene directly. Then from benzene, somebody would decide to add a methyl group to form for us methyl benzene, like that. Obviously using a halogen, so not an alkyl halide in the presence of a halogen carrier. Then from here, somebody would end up producing for us benzoic acid using a strong oxidizing agent, and then they heat. Then finally would produce for us the amide. Somebody would have thought of that. But it has a problem. The problem is that the number of steps are very many. They're actually more than 6. Or they can be exactly 6 or more than 6. So this is number 1. Somebody will do that number 1. Number 2, after producing that, they would come here number 3, number 4, number 5, number 6, and number 7. So those steps are actually very many. The steps are very many. So the second synthesis is correct, but it is inefficient. It is correct but inefficient. So what you do, you have to think in your brain and get the shortest possible route. And the shortest possible route would be from this benzene diazonium chloride. We would first of all produce, that. Then after we would produce that, then it brings us directly to that. So whenever you're carrying out a synthesis, look for those steps that are going to give you the least number. Look for those reactions that are going to give you the least number of steps. And that way your synthesis is going to become very, very efficient. I hope that has been understood. There are people who want to take screenshots, you can do so. But then after the lesson, you can go back and watch the video on YouTube. Then you see a way of summarizing the information. You can write it down and you do more practice. Because I'm very sure this concept is going to be tested. You can also take a screenshot of that. Somebody can take a screenshot of that and just use it, decide to use it as your wallpaper or as your DP on WhatsApp, even if it is for 1 week. By the time it finishes 1 week as your WhatsApp DP, you should have mastered everything on it. You can use it as your profile photo, your wallpaper on your phone. Okay, so that is number 5. So organic synthesis is very rich, very, very, very rich. And we may not even finish the questions, but there are very more. You can even do 2,000 questions. That was number 5. We can go for number 6. Can look at question 6. Question 6, we are saying we are moving from phenol we are moving to that compound. Now somebody can look at that compound on first sight and be like, can they really bring that question in exams? But the synthesis is actually very simple. Now the trick that you're going to use for this is that you're going to use a retrosynthesis. That is the only trick that can bail you out of this number. When you look at this question here, you look at these compounds, these things that are present within this functional group. When you look at them critically, you're going to realize that they are actually coming from a reaction between a carbonyl compound plus sodium hydrogen sulfide. Reaction between a carbonyl compound and sodium hydrogen sulfide. So the carbonyl compound most likely is going to be this one here. Cyclohexanone. That is the carbonyl compound we are going to produce. But how am I going to produce that carbonyl compound? We can produce it from an alcohol. And which alcohol are we going to produce it from? It can be produced from an alcohol which is of that form, OH. So you can see that the thing is coming from, we are already going to phenol. Then from phenol, you can produce this kind of alcohol. You looked at that under the addition reactions of phenol. So here, I'm going to add hydrogen in the presence of nickel catalyst at a temperature of 200 degrees Celsius. That is the only condition that can remove for us the pi electrons on phenol. So after that, we can convert that to an alcohol using an oxidizing agent. So we can use an oxidizing agent, manganese 4. So we can use manganate 6, manganate 7 ions, potassium permanganate, then we heat. And then from here, what are we going to add? From here, what are we going to add? We said we are going to add sodium hydrogen sulfate. So we shall add sodium hydrogen sulfate. And the moment you add sodium hydrogen sulfate, you would have formed that compound. So in that way, a retrosynthesis would be able to help you very well, because the other final product we are having is a little bit very complicated. So that retrosynthesis can help you to be able to do it. So I have done it from behind, from the final product, going back to the first product. So you can see. So I've already finished synthesizing that compound. But it's a retrosynthesis that has bailed us out. It was not for retrosynthesis, would have been finished. So that is number 6. Should now go ahead and look at number 7. People are already running away. Okay, so make sure you're following our social media platforms, because that is where you can be in position to be updated on everything we are doing. We are having TikTok. After this, go and follow our channel on TikTok. BioChem Online Clinic. All of them are named the same name. Then you go on YouTube, make sure you subscribe. We need those subscriptions to help our media visibility to increase. So give us that subscription. Then you can also check on our WhatsApp channel at BioChem Online Clinic, and we shall be there. Okay, so we are going for the next question. So we are done with question 6. We can look at question 7. Question 7. What is question 7 saying? Question is saying we are moving from benzoic acid. We are moving to which compound? To this compound. It's called N-methyl N-methylamminobenzene. N-methylamminobenzene. So how are we going to move to that compound? So what is the chemical, the structural formula of benzoic acid? We all know that one. Eh? The structural formula of benzoic acid is that. Then the structural formula for N-methylaminobenzene. Now this one, we looked at it when we were naming amines, when we were doing the nomenclature of amines. That lesson for amines is in our Google Drive. So we did that, and we say that some complex amines can be named like that. So you have, this is N-methylaminobenzene. That is the compound. Okay, so we are moving from benzoic acid straight up to that compound. So how are we going to get there? The best thing that can also help us in this is we should first be able to note where is this final product coming from. This final product is coming from phenylamine or from aminobenzene. That compound is coming from aminobenzene. So how are we going to move from benzoic acid straight up to aminobenzene? The first thing we can do is that, and we say that aminobenzene can come from nitrobenzene, isn't it? So we can first of all remove that. We can remove that carboxyl group. We can remove it. We can do away with that by using soda lime. Soda lime, and then we heat. Then after doing this, we can have nitrobenzene there. We can form nitrobenzene. And that reaction, we said, how do we form nitrobenzene? You looked at it under the electrophilic substitution reactions of benzene. So here we said you're going to use concentrated. Let me just write the concentrated ones because we don't have space. So I'm just going to say concentrated sulfuric acid and then concentrated nitric acid. Between which temperature? 55 to 60 degrees Celsius. And then from here, I can move to phenylamine. From there, you can move to phenylamine. What do? You use tin in the presence of concentrated hydrochloric acid. And then you're going to heat. And then after that, from here, you can now move to the final product. But I remember saying that this reaction, that reaction is going to fall under the alkylation reaction of amines, of aminobenzene that we looked at. So in that case, what are we going to do? We are going to add an alkyl halide. So we shall have CH3, Cl, and then you're going to heat, and you're going to form that final product. Then also, now sometimes some books have this. In some books, you can use iodomethane. But when you use iodomethane, there is no need of you heating. The reason why you don't heat, because the carbon halogen bond is actually longer because of the larger ionic atomic radius of iodine. That makes the carbon halogen bond longer, making it stronger, and so it is more reactive. So when you're using that, you don't heat, but you can just use chloromethane and then you heat and you'll form that final product. So that is the synthesis we have for number 7. So keep your synthetic routes as short as possible. Use the correct reagents. You're seeing that? And on top of using the correct reagents, make sure that, that the reagents you use are the reagents that you're going to use are actually within the scope of the chemistry syllabus. Don't use very complicated reagents that your teachers won't understand. The few reagents you have learned can do a lot for you compared to you knowing very ambiguous and very heavy reagents that won't be able to help you. So use simple reagents that can easily be understood. So that is number 7. Okay. So we can look at number 7. For those of you who have been following us from first term's holidays, we have actually finished looking at the whole of organic chemistry. By the way, we have finished all the organic chemistry, and those lessons are available on our Google Drive. So for those that are joining us for the January intake, you can be in position to find those lessons. So we are doing number 8, not number 7. Those lessons are available on our Google Drive. For those that are joining us for the Jan intake, please, you can be in position to access them. You guys, please stop playing around with the screens. For people who have just joined, don't tamper with our screen, guys. Don't tamper with our screen. Please don't tamper with our screen. Don't touch that pen-like structure at the left-hand side of your screen. Those lessons are available on our Google Drive. You just have to subscribe for the January intake and you can have access to the Google Drive. You can listen to those lessons up to February until you go back to school. You can have access to that Google Drive and enrich your academics. So let's look at number 8. Number 8 is saying we are moving from propene to 2-amino 2-methyl 2-methyl propane. Okay, our time, we really have to increase our speed a little bit, but it's okay. 2-methyl propane. So in this case, we can draw the structures of this so that we compare the two and see what we need to add. The chemical formula of propene is CH3, C double bond, CH2, H. Then we are moving from that to 2-methyl propene. That's 2-amino 2-methyl propene. It means that these amino group and then the methyl group are substituent groups attached onto propane. So you're going to have something like this: CH3, C, NH2, CH3, CH, CH3. That is 2-amino 2-methyl propane. So how are we going to do that? So in this reaction, when you look at the difference, you can see that it is involving an increase in the number of carbon in the number of carbon atoms. And the number of carbon atoms is increasing in a branch. There is a branching that has been introduced. We are not increasing it linearly, but there is a branch that has been introduced, meaning at a particular point in our synthesis, we are going to use a Grignard's reagent. But this Grignard's reagent is reacting with a carbonyl compound for us to be able to achieve this kind of structure at the end of the day. So what are we going to do? So from the alkene, we can synthesize a carbonyl compound. How do we do that? We first move to an alcohol. How do we move to the alcohol? By now you should be in position to remember the reaction of alkenes with acidified water gives us alcohols. So I'm having acidified water, then you're going to warm. You're just going to warm. Then after forming that, we are going to use an oxidizing agent to form a carbonyl compound. Then we heat. Then after that, we shall form now our carbonyl compound. Then from here, we are going to add a Grignard's reagent. We are going to add a Grignard's reagent to form that. Which Grignard's reagent should we add? CH3, MgBr. And then after this, what are we going to do? We are going to hydrolyze it. So from this CH3, CO, MgBr, CH3, we are going to hydrolyze that using aqueous ammonium chloride. Then you will form a tertiary alcohol. So after you forming your tertiary alcohol, you can halogenate that alcohol. The easiest is by using PBr5. Phosphorus, you can use that, or another person can decide to use PCl5. Another person can use PCl3. The end result is that we shall just halogenate that alcohol. So you're going to form CH3, CBr, CH3, CH3. And after forming that, the last step now is that we are going to replace that. We are going to replace that with ammonium. We are going to replace that with an amino group. So what are we going to use? Usually we use excess alcoholic ammonia. We use excess alcoholic ammonia, and then we are going to heat. And usually the heating is done in a sealed tube. So you'll form CH3, NH2, CH3, CH3. And you would have produced that compound. Somebody saying, you said we use the shortest routes, but I remember we can hydrolyze propene in the presence of mercury sulfate at 60 degrees Celsius. That is also a good observation. You can also use that. And you will be able to have the shortest route. But the route I've also used, I think, is giving us about 6 steps. Let us count. This is 1, 2, 3, 4, 5, 6. We are having 6 steps. But this girl's idea is wrong. She's saying that we can hydrolyze propene in the presence of mercury sulfate at 60 degrees Celsius. That reaction is only done for alkynes, not alkenes. If it was propane, we would have done that. But we are having propene. So that is why I have taken that route. But if it was propine, you would have moved directly to that, to the compound that we are having. So the one of mercury sulfate cannot work. It cannot work. Guys, let's not play around with our screens. Gloria, stop what you're doing. There are people who have just failed to understand. So that is the synthetic route that I have used. It's giving me 6 steps, and those steps are okay. Those 6 steps are okay. So the following Sunday, the next Sunday, I think after elections, we are also going to have what is called organic analysis. So make sure you also attend organic analysis. And by the time I'm done, all the concepts you will need in organic chemistry, you would have covered them. Then now the other things will follow. I'm trying hard to finish my physical chemistry at least by the end of January, and we are going to finish. We are going to finish. So you can, somebody wants to take a screenshot of that, it's okay. Now this video, this lesson is going to be uploaded online. I don't know why you guys are. You guys will take those screenshots from it. It's okay. Let me give you guys to take screenshots. But what I'm going to do is that I'm going to share the entire PDF of this work on the WhatsApp channel. So to save time, let us just do that. I'm going to make sure I put the PDF on the WhatsApp channel. So you can first take a screenshot of that if you're taking. How do you access the work on the Google Drive? You contact me. You have to subscribe for January. That is when you can access the work. Okay, so let's look at the last question. The last question on that first part, that is question now. It's going to be question number what? Question number 9. Eh? Question 9. Question 9 is saying we are having this compound. From this compound, I am synthesizing this compound. Now, if you're seeing this compound for the first time, you're going to become very scared. It is an azodide. It's an azodide. So we are moving from that up to that compound. Now, the moment you look at that compound, don't get scared. Sit down, take a deep breath, and remember, where have you ever seen that compound from? This final compound, we studied it when we were looking at the coupling reactions of phenol. When we're looking at the coupling reactions of phenol, if you have covered it in your schools, you'll be in position to remember. Whereby we say that phenol, the coupling reaction of phenol. So in this case, you're going to have phenol reacting with a benzene diazonium salt to form for us that compound. So it falls under a coupling reaction of phenol. So what is your mandate and duty to do in this synthesis? You can either first of all start by producing, you can produce phenol, or you can produce benzene diazonium chloride. Or you can produce benzene diazonium chloride. So there are two options that you have. But the easiest would be for me to produce benzene diazonium chloride. How? I can convert these to aminobenzene. It can be converted to aminobenzene. But you see that conversion of that amide to aminobenzene is reducing on the number of carbon atoms. You're seeing that because the number of carbon atoms has reduced, the reaction we are using is called Hofmann's degradation of amides. So that when you use bromine in the presence of concentrated sodium hydroxide, and then you warm, you do not heat, you have to warm. And then after you're going to form that phenylamine or aminobenzene. Then from aminobenzene, you can go ahead and produce benzene diazonium. You can go ahead and produce benzene diazonium salt. You can produce your benzene diazonium chloride. How do you do that? Said you're going to use sodium nitrite in the presence of concentrated hydrochloric acid between 0 to 5 degrees Celsius. Then from here, you can produce that compound directly. You can produce the compound directly. How can you do that? You just have to use phenol. You react that with phenol. But we say that the coupling reactions usually take place in an alkaline media. Then you add the OH ions to show you that the reaction is taking place in an alkaline medium, and you would have produced that product in just 1, 2, 3 steps. But there is also another way you can produce that in a bigger number of steps. You can also produce that in a bigger number of steps. We can first start also by producing phenol. You can produce also phenol. How? I can have this benzene, we can have this amide. Then this amide can be converted to a carboxylic acid. We looked at that reaction and we say that here we can hydrolyze the amide with water. And once we hydrolyze it with water, it can be converted to a benzoic, to a carboxylic acid. And then from there we can decarboxylate, remove the carboxyl group and we form benzene. Then from there we are now aiming at phenol. From there we use soda lime to decarboxylate. Soda lime, then we heat. Then after that you can form that. We can form chlorobenzene. Remember, we are aiming at producing phenol. So here we shall add chlorine in the presence of a halogen carrier, that is aluminium chloride. Then from here, what are we going to do? We are going to form sodium phenoxide. To produce sodium phenoxide, what do? We need aqueous sodium hydroxide 350 degrees Celsius, 360, sorry, then 150 atmospheres of temperature to form sodium phenoxide. And then sodium phenoxide can give us phenol. We just have to hydrolyze that using a dilute acid, and to give us phenol, shall just use dilute hydrochloric acid. Then from phenol, I can move to the final product, the azodine. Can move to the final product. Can move to that final product. You can form that final product. But how are you forming it? You're now going to add a benzene diazonium salt. In the presence of, in an alkaline condition. But these steps are how many? 1, 2, 3, 4, 5, 6. The steps are 6. But the other one was just giving us the same reaction in only 3 steps. So now the first one is more efficient compared to the second one. So in case you're having 2 ways to do it, you choose the ways that give you the least possible steps, and then you would form that compound. So that is number 9. Okay, and so we have actually finished the first page. We have finished the first page. I thought we were going to finish all these numbers today, but my God. Now what I'm going to do is that I'm going to do the next how many numbers? 1, 2, 3, 4, 5, 6, 7. There are 7 more numbers I'm going to do, but these other 7 are easy. The hardest ones, the toughest ones that were available are these, the first 9 numbers are the hardest. But these other numbers are very simple. So I'm going to run through these up to about 10:30. I'm going to run through these remaining numbers. There are 7 numbers. Then the remaining numbers, I'm going to give it to you people as an assignment. So make sure those numbers are discussed in the group. Once you finish doing the number, you inbox it to me on WhatsApp. I mark it and I send for you your solution. Then you can post it in the group for other friends to see. And we do that. So let me do the remaining 7 numbers and then we finish. So that reaction is done. That synthesis is done. So we can look at number. We are done with number. That was number 9. Eh? We can look at number 10. Number 10. On number 10, we are moving from this compound. We are moving from that compound and we are moving to this compound. That compound is an alkyne. And by virtue of you seeing that, should come to your mind, how am I going to convert that to an alkyne? The first thing, you first move to an alkane, then you first move to an alkene. Then from an alkene, you move to an alkane. So from here, what am I going to do? I can first convert that to an alcohol so that I form my alkene. So how do I convert that to an alcohol? I use sodium hydroxide, and then I'm going to heat. After doing that, I'm going to form an alcohol. Please, guys, stop playing around with our screen. Then from here, I'm going to dehydrate that alcohol using concentrated sulfuric acid at 180 degrees Celsius. Then I'm going to form an alkene. Then this alkene, we are now going to add a halogen. We are going to add bromine, obviously in the presence of carbon tetrachloride. Then after you would form that compound, then after the final thing you're going to do, you're going to dehalogenate using excess potassium hydroxide in the presence of ethanol. And then you're going to heat, and you would have formed that compound. you would have formed that compound. That one is way much more easier. It's way much more easier. Or another person would have said, let me give another alternative. Another person would have said that from the alkene, from this alkene here that we have formed, from the alkene, what I can do, I can first start by forming an alcohol. Guys, let's stop playing around with the screen. We can form an alcohol like that. That is the alcohol we have formed. Then after, how are you forming your alcohol? We are using acidified water, and then you warm. And then after that, what are you going to do? After that, you're going to form a carbonyl compound. How are you forming the carbonyl compound? Using an oxidizing agent, a strong oxidizing agent. And we said you always have to heat. Then from here, you're going to form a germinodihalide by adding PCl5. When you add PCl5, you would have formed a germinodihalide. You will have that. Then the last thing you can do is to dehalohydrogenate. Dehalohydrogenate. Still, the dehalohydrogenation is going to give you that final product. This second one is taking us how many steps? It's taking us 1, 2, 3. The dehydrogenation, you're using potassium hydroxide in the presence of ethanol. But obviously, it's going to be excess. And then we are going to heat. So this one is taking us 6 steps. The second alternative is taking us 6 steps. The first alternative has taken us how many steps? Has taken us 1, 2, 3, 4. Has taken us 4 steps. So the second alternative is actually it's a better alternative. The first alternative, sorry, is the better one. The one that is giving us the least number of steps. The one that is giving us the least number of steps. So that one is okay. Can just take those screenshots if you're taking. But I'm going to give you I'm going to put the screenshots, the document of this. I'm going to put them in the WhatsApp channel after the lesson. So let's look at the other number. It's now going to be number 11. Number 11 is saying CH3, COCl. Then you're moving to CH3, CH, then Cl, and Cl. Aha. So we are moving to that compound. It is a germinodihalide. And we say that a germinodihalide, these germinodihalides usually are formed from carbonyl. They are usually formed from carbonyl compounds. The reaction of carbonyl compounds with PCl5. So we are going to convert that acid chloride into a carbonyl compound. First and foremost, we can first react it with water to hydrolyze that to form a carboxylic acid. So we shall have CH3, COOH. Then after that, what we are going to do, we are going to convert that to an alcohol. Shall convert that to an alcohol. by using a reducing agent, lithium aluminium tetrahydride, in the presence of dry ether to form for us CH3, CH2, OH, that is ethanol. Then after this ethanol, we shall convert it to a carbonyl compound. Remember, we are going to use what? A weak oxidizing agent, because we are using a primary alcohol. And if we use the strong oxidizing agent, the primary alcohol would be oxidized directly to a carboxylic acid. But in this case, we are stopping at an aldehyde. Then from here, the last step is that we shall add PCl5. And after adding PCl5, you would have formed the germinal dihalide. You would have formed the germinal dihalide. So that is the synthetic route. Look at the final product, see where it is coming from. And through the series of reactions that you have studied in organic chemistry, arrange your work logically and come up with the final product. Come up with the final product. That is number 11. Let's look at number 12. Let's look at number 12. Number 12 is saying we are moving from chlorobenzene. We are moving straight up to methylbenzene. We already looked at this under the manipulation of the benzene ring when you look at our organic synthesis part 1. So the first thing, this one is very simple. The first thing we are going to do is to remove this. But the easiest way of removing that is by first of all converting it to phenol. So we can first form sodium phenoxide by doing what? We shall have sodium hydroxide, 360 degrees Celsius, and a temperature of 150 atmospheres. Then after, we are going to hydrolyze that using a dilute acid. Hydrolyzing that gives us phenol. And then after forming phenol, we can remove the hydroxyl group on phenol by reacting it with zinc dust. And then we heat. And then after that, we shall just form benzene. And after forming benzene, you're going to add the alkyl group, a methyl group, onto the benzene ring by using chloromethane in the presence of a halogen carrier. And you would have formed your final products. You would have formed your final products. So that one is okay. It falls under the manipulation of the benzene ring. We are remaining with 3 other questions to go. 4 other questions to complete. So let's be patient and avoid going offline. That is number 12. Let's look at number 13. Look at number 13. Number 13 here is saying we are moving from this compound CH3, CH double bond, CH2. Then we are moving straight up to this compound CH3, C, triple bond, C, CH3. When you look at those compounds, immediately you're going to see that there is an increase in the number of carbon atoms. There is an increase in the number of carbon atoms by 1. So what are you going to do? I am going to involve a reaction that helps me to increase on the carbon on the carbon chain. But obviously here I'm seeing an alkyne at the end of the final product is an alkyne. So I'm going to use that reaction of alkynes with sodium in the presence of dry ether for us to be able to increase on the carbon chain. So I can first convert that to an alkyne, first by adding bromine in the presence of carbon tetrachloride to form CH3, CHBr, CH2Br. Then I'm going to dehalohydrogenate this. Dehalohydrogenating it using excess potassium hydroxide in the presence of ethanol. And then I heat. So I'll form CH3, C, triple bond, CH. Then after I am going to increase on the carbon chain. But the first thing we said is that we first of all add sodium in the presence of liquid ammonia. Liquid ammonia for us to form that compound. Then after, we are going to add an alkyl halide. The alkyl halide we can add is CH3Br. And then we would have formed the final product. So that one there is involving an increase in the carbon. It's involving an increase in the carbon chain. That one is involving an increase in the carbon chain. So that is our question 13. So that one is quite very obvious. Then let's look at question 14. Look at question 14. Question 14 is saying we are moving from this compound CH3, CH2, Br, and then we are moving to that compound CH3, CH, CH3, OH. That is an alcohol. So when you look at those two compounds, immediately you're going to notice that there is an increase in the number of carbon atoms. The number of carbon atoms has increased, right? So what are you going to do? I am going to have one reaction that is going to increase for me the number of carbon atoms. Obviously, I'm starting from an alkyl halide. And the easiest way for me to increase starting from an alkyl halide is by having a nucleophilic substitution reaction, whereby we shall have CH3, CH2, CN being formed. But we shall use potassium cyanide in the presence of ethanol. And then we heat. That one is going to form for me that nitrile. And then after forming that one, we are going to convert this straight up to a carboxylic acid. We shall convert it to a carboxylic acid by using acidified water. And then we heat. After that, we shall form the carboxylic acid. CH2, COO, OOH. Then that carboxylic acid, we can convert it to an alcohol by using what? Using a reducing agent. Lithium aluminium tetrahydride in the presence of dry ether. So it is going to give me an alcohol, CH3, CH2, CH2, OH. But you look at the difference between where we are and the final product. In the final product, the hydroxyl functional group is located on carbon atom number 2, but not carbon atom number 1. That means I can first convert this to an alkene. So I'll have CH3, C, H double bond, CH2 by obviously using concentrated sulfuric acid, and then I'm going to heat it at 180 degrees Celsius. Then from there you can add acidified water to form the final product. You add acidified water and then you warm, and it will give you that final product. It will give you that final product. So you can see we have increased on the carbon chain and after increasing on the carbon chain, we have changed the hydroxyl group to position number 2, and this reaction has helped us. So the next time you're having a change in the position of the hydroxyl functional group, you can use acidified water and then you warm. So we are remaining with 2 more numbers to go. By exactly 10:30, we are stopping the lesson. By exactly 10:30, the lesson is getting done. That is number 14. So we look at number 15. Look at number 15. Look at number 15. Number 15 is saying from ethene, we are having ethene. Let me just draw the structure. We are converting ethene. When you look at number 7, we are converting it to that compound, ethanoic acid. That one is actually very easy. You're going to convert that to ethanoic acid. But where is ethanoic acid coming from? Ethanoic acid is coming from an alcohol. So we can convert that ethene to an alcohol. How can we convert it to an alcohol? By using acidified water. You can use acidified water and then you warm. Then after doing that, you will form an alcohol. That is ethanol. Then ethanol is going to be oxidized to a carboxylic acid. And we say that when you're oxidizing a primary alcohol to a carboxylic acid, you use a strong oxidizing agent. So we're having that strong oxidizing agent and then we heat. It will convert that directly to a carboxylic acid. And number 15 is done. Number 15 is done. What about number 16, the last number? We're having only 2 minutes to complete the lesson. Number 16, which is our last number. We are converting benzene to benzoic acid. That one is very easy. Benzene to benzoic acid. Benzoic acid, we said, can be prepared from methyl benzene. Oxidizing methyl benzene using a strong oxidizing agent. So we shall first of all form methyl benzene by alkylating benzene. So you'll have, in the presence of a halogen carrier. Then after that, you can convert that to benzoic acid by using a strong oxidizing agent. That is that. And then we heat. And we would have formed benzoic. We would have formed benzoic acid. We would have formed benzoic acid in that way. Now, before I end the lesson, I want to encourage you people. Organic chemistry is mastered by practice. Master it by practice. The more you continue doing these reactions, the more they become part of you. And the more you continue doing these synthetic numbers, the more you're going to find similarities happening. So you're going to end up having similar concepts coming up your way. So do more practice. Then the following time, we are going to finalize with the last concept of organic chemistry. We are going to look at organic analysis.